Hello everyone. This video demonstrates the simulation of a DC to DC buck converter using average state model. So we'll be constructing the DC converter, buck converter using average state model. Let us now open the Simulink. And we will open a Planck model. We have already seen the simulation of a buck converter using switch model, but here we are going to see the simulation using the average state model. So now we have opened the new model, new untitled Simulink model, and we are going to construct the buck converter whose specifications are given in the table. And the average state model, it is given by the two equations, dIL by dt and dV naught by dt. So these two equations we are going to construct using the Simulink. So we are now going to implement the first equation, dIL by dt, which has the summation of the two terms divided by L. So we are taking the sum block. To the sum block, we have to give the input V in. So that V in, it is given as 24. And we are going to connect that with plus sign. And we need to have V naught, that is V naught, which is given with a minus sign. And we have to choose the V naught annotation to represent the signal name. And we have that is V in, it is multiplied by the duty ratio T. So we have to include a gain block to which we are feeding the input V in. And the output of that gain will be T into V in. D, it is given in the table as 0.5. And the output of the sum block, it should be it is divided after dividing that by L, we'll be getting the dIL by dt, and that should be given to the integrator. So we need to have a 1 by L block between the sum block and the integrator. So that we can give with the help of a gain block. In the gain will be having 1 divided by L. L value is given as 1.5 millihenry. So we are feeding the value of L. This block is nothing but 1 by L. So output of the sum block and divided by L will give the dIL by dt. And next we have to construct the second differential equation, dVc by dt, which is nothing but IL divided by C minus V naught by RC. So we need to have again another sum block which is equal to that sum block will be having its input as IL, and then again minus V naught by R. After that, we will be dividing that by 1 by C. That is IL minus V naught by R divided by C. C value it is given as 250 microhenry. And so we are dividing the output of the sum block by C, and the output of that gain, it is given to an integrator. So the output of the gain block will be nothing but dVc or dV naught by dt. That will be given to an integrator, so that we will get the output as output of the integrator as V naught. Output of this integrator will be V naught. This V naught we are going to connect it to the first sum block, and that V naught divided by R will be given to the second sum block. So we need to have 1 by R. For that, again, we are going to take the gain block, and the gain block is connected to the sum block. The gain of this block will be 1 by R. R value, it is given as 3 ohms. So 1 by 3 is the gain of that block. This gain is nothing but 1 by R. Now we can display the output voltage, and we can also see the output voltage using a scope. And we also use two workspace in order to get the time domain specifications, and we'll be renamed that as V naught. So again, we will be seeing the display waveform and the two workspace for the inductor current also. Now we can run this model for a time of 0.06. So we are running this model for 0.06 second. So we can see that the expected output voltage, which is 12 volts, which we are getting it as 12 volts with a duty ratio of 0.5. The output voltage, it is seen in the scope, which is going to have some overshoot. And similarly, the inductor current, whose value is 4 ampere. And we can measure the time domain specifications by feeding code in the workspace. The code is info equal to step of step info of out.v0.data, comma out.v0.time. So with this command, we will be able to get the time domain specifications for the modeled buck converter. So we have obtained the values of rise time, peak overshoot, then settling time, everything we got. So these are all the time domain specifications with the given specifications of the DC to DC buck converter. So likewise, we can take the time domain specifications with the help of which we can analyze the system. So by changing the L and C value, we can find the changes that are taking place in the time domain specifications. So that can also be done. So we can see that the settling time and the maximum, the overshoot, peak overshoot, everything, we can compare the values with the scope. So this is the simulation using the average states model. Thank you for watching this video.